Hello, my name is Devin Jean. I'm a PhD student at Vanderbilt University. Today I'll be demonstrating Phone IoT, a tool we've developed to introduce high school students to the Internet of Things. While many schools have computing labs and makerspaces, the majority still do not. However, most students have smartphones and various sensors. And with Phone IoT and NetsBlocks, we can make them available for students' programming projects running in a web browser on their computers. NetsBlocks is an educational block-based programming environment similar to Scratch and Snap, but with a focus on networking and distributed computing. NetsBlocks has previously been shown to enable students to create distributed programs with little to no prior programming experience. In NetsBlocks, these services are provided by remote procedure calls, or RPCs, and message passing. Phone IoT uses these same networking primitives, so any student already familiar with NetBlocks will feel comfortable using Phone IoT to access sensor data and create new projects using it. On the technical side, the Phone IoT app collects live sensor data from the device and serves it to the NetsBlocks server over UDP. NetsBlocks clients interact with the server via RPCs and messages. There are two primary modes of accessing sensor data, either by explicit on-demand request with an RPC, or by requesting a continuous stream of data via periodic messages from the device. For example, the Get Magnetic Field RPC shown here returns the current value from the sensor, while the Listen to Sensors RPC turns on sensor streaming. In this case, we'll get location messages every 2 seconds and magnetic field messages twice a second. We receive these sensor updates with When I Receive blocks, with the sensor values being message fields. Phone IoT also lets users control a fully customizable GUI on the device. This canvas is initially empty but can be populated with controls such as image displays, toggle switches, buttons, text fields, or even virtual joysticks, all entirely from NetsBlocks. These controls are linked to the student's program with the same message passing system, making them a convenient and interesting way to integrate the phones to a student's NetsBlocks program. For instance, students can turn their phones into a game controller or run a group chat. The possibilities opened up by Phone IoT are up to the student's imagination, which we believe will lead to compelling and highly engaging projects. To begin using Phone IoT, navigate to editor.netsblocks.org. Every operation with Phone IoT requires the device's ID. Because of this, we'll store it in a variable called device for convenience. Next, launch the Phone IoT app on your mobile device, open the menu at the top left, and click Connect. You should see a notification at the bottom of the screen saying you successfully connected to the server. At the top of the menu, you'll see an ID and password. We'll need to copy the ID into the device variable we just created. Then, under the Networking tab in the NetsBlocks editor, grab a Run block. In the first dropdown, select the Phone IoT service, and in the second, select the Set Credentials RPC. Here, we'll give it the device variable, as well as the password. We can now click on this group of blocks to execute it, which will connect to the device. Once connected, we can grab a call block from the Networking tab and set it to the Get Accelerometer RPC. Once we've connected to the device, we can supply the device variable to the Get Accelerometer RPC and click it to get instantaneous values from the sensor. This could be performed in a loop to get continual data. However, in that case, it's more convenient to use a continual sensor stream with the Listen to Sensors RPC. By providing it the device and a list of pairs representing each sensor and interval, we can get continual sensor updates from the device using NetsBlocks' message passing system. In order to receive these messages, we'll need to create a new message type called accelerometer and provide it with the X, Y, and Z fields. Next, we grab a When I Receive block and set it to the accelerometer message type we just created. Anything we put under this block will be executed once every time we get a sensor update on the accelerometer. By using a simple say block, as well as some rounding logic, we can create an output that'll show the current accelerometer data of the device as we update twice per second. Using the same technique of sensor update events we just introduced, we can easily integrate our phone's accelerometers to control the NetsBlocks state. For instance, we can use the accelerometer to control a ball rolling around in a game environment. Here's a simple game we put together where you use the accelerometer to control the ball rolling around through a field of holes by tilting your device. The objective is to get to the upper right-hand corner where there's a green flag without falling into a hole. We'll now introduce the second side of Phone IoT, which is the custom controls canvas. To begin, set up the device variable and set credentials just the same as we did before. When the Phone IoT menu is not open, the custom controls canvas covers the entire screen of the main display. To make it easier to exchange projects between phones having different aspect ratios, this space is broken up into a relative scale, with 0, 0 being the top left-hand corner of the screen and 100, 100 being the bottom right. A good thing to do on initialization is to clear all the controls that might already be on the screen. To do this, we can use the Clear Controls RPC under the Display tag. To add a new control to the display, you can use one of the RPCs under the Display tag. Here we'll add a button. We'll set the position of the button to 5, 5, meaning it will be near the top left-hand corner of the screen. We set the width to 45, meaning the end of the button on the right should be in the middle of the screen. The text field can be used to control what's displayed on the button. The options field is used to specify other behaviors and visual appearances for the button. We'll cover these later. If you run this group of blocks now, you'll see that a button appears on your screen. However, when you press it, nothing happens. To receive click events from the device, we need to create a new message type. We'll call it button press. Next, we need to instruct the button to send this message when it's clicked. To do this, we have to add an optional parameter called event. We give the event value the name of the message to send, in this case, button press. Now that everything is configured the way we want, we need to call the Listen to GUI RPC to actually begin receiving messages. This is only required to be called once, and you could do it before adding controls. If we rerun this group of blocks, we'll see that the button is recreated as it used to be. However, now when we press the button, the sprite in the browser says hello. The options parameter has many settings you can use to control the physical appearance of the button and some of its behaviors. One of these is the color argument, which can change the background color of the button. Colors are represented by an integer. You can get the color code for any RGB color using the getColor RPC under the Utilities tag. If you look at the button on the display, you'll see that the text is small and hard to read. To fix this, we can pass the optional font size parameter. The default font size is 1, so we can change it to 2 to make it a little bit more readable. Remember to rerun the code blocks to get the updated view. There are many types of custom controls, including buttons, toggles, text fields, labels, image displays, and even joysticks. Each of these has its own set of optional parameters. To get the list of optional parameters for any given type, you can select the RPC in a call block, right-click on the call block, and select Help. This will give detailed information about how to use the RPC, as well as the optional parameters. In this project, we combine both sensors and display to create a simple fitness tracker. We use an image display to show a map plotting the user's location, a text field to show the total distance traveled, and 2 buttons to start and stop the tracking. We can use the getLocation RPC to get the initial location of the device, and use some RPCs from the Google Maps service, a pre-existing service in NetsBlocks, to get a map of the area. When we add a custom control to the display, it returns an ID that can be used by other RPCs to modify the content. Using this, we can set up the GUI to an initial state, request sensor updates from the location sensor, and continually update a visual display on the mobile device to match the NetsBlocks stage running in the browser. When we receive a location update, we can use RPCs from the Google Maps service to convert the latitude and longitude into screen points and draw a path to the new location. We can even use the bearing field of the location sensor to point in roughly the right direction. Other RPCs from the Google Maps service are used to get the traveled distance, along with some custom averaging logic to mitigate GPS position noise. What you see is an example of me connecting to NetsBlocks with mobile data turned on and walking around a few blocks. One of the driving motivations for integrating Phone IoT with NetsBlocks is that it allows students to use all of the pre-existing NetsBlocks services. These services connect to a large number of internet-based APIs, such as getting weather information, Google Maps, historical data, or even controlling robots remotely. Using some of the same GUI techniques we just introduced, we can make a remote control that controls a physical robot rolling around on the ground. These types of possibilities are why we think Phone IoT will make highly engaging projects for K-12 audiences. Thank you for your attention during this demo. You can visit netsblocks.org for more information about NetsBlocks. You can also try out Phone IoT by going to editor.netsblocks.org. The mobile app is available free of charge on Android through the Google Play Store and will soon be released on iOS as well. At this point, we would like to thank our sponsors at the NSF and NSA for their continued support and allowing us to continue our ongoing research into furthering high school CS education.